Hello, my name is Andrei Suli. I shall be teaching this course on numerical solution of differential equations to you. So you see the word y on this first slide, and so the purpose of this lecture 0 is to motivate the course and try to explain why exactly we are interested in the numerical solution of differential equations. So numerical solution of differential equations is a very rich and active field of modern applied mathematics. The growth of the subject is stimulated by ever-increasing demands from the natural sciences, engineering, and economics to provide accurate and reliable approximations to mathematical models involving ordinary differential equations and partial differential equations whose exact solutions are either too complicated to find in closed form or, in many cases, they are not even known to exist. So what you see on the slide are two situations when you might use numerical methods for the approximate solution of partial differential equations in engineering applications. Perhaps you might be interested in modeling the flow of air around an aircraft, or perhaps modeling the flow of air around a car. So on the next slide, I'm going to describe to you the numerical solution of a problem that comes from solid mechanics, but so that you understand what exactly is happening, let me try to illustrate the physical situation. So I have a sheet of paper in front of me, but imagine for a moment that this sheet of paper is a rigid body. So in this, let's imagine, rigid body, there is a pre-existing crack, which you can see here. So the physical situation you might be interested in is what happens if you push one of the sides of this rigid body downwards and pull the other side of the rigid body upwards. Which way will this crack propagate? So obviously I can carry out this experiment with this sheet of paper, so let's do it. So the crack propagated through the body. The question is, could you simulate this problem numerically? So what you see here is a numerical simulation of this experiment on the left-hand figure. So you don't see the pre-existing crack because it's not indicated. What you have seen is how the crack evolves as the body undergoes this deformation. You pull one side up and the other side down. So you see this crack that evolves from the crack tip through the body. So in the second experiment, a hole was drilled in this rigid body, and you ask yourself the same question. There is a pre-existing crack, which again is not indicated. Which way will the crack propagate this time? And so what you see is that instead of running straight through the body, the crack finds the weakest spot, this hole in the object, in this rigid body, and runs into this hole. So what has happened here is a complicated set of partial differential equations coming from solid mechanics has been solved numerically. And as you can see from this example, using numerical models, you can carry out simulations by solving partial differential equations. So what I'm showing you on this slide are the computational grids that have been used in order to carry out these numerical simulations. In the first case, when there is a pre-existing crack at the top and a straight crack evolves running through the body, and what you see on this picture is a triangulation of the computational domain that evolves with the crack as the crack runs through the domain. So it is a time-dependent problem, and you can see also the evolving computational mesh in this second example when we drill the hole into the computational domain. So the foundations of the theory of differential equations are really quite old, and they go back to the work of Newton, who introduced his fluxional equations in the 1670s, and the subject was subsequently developed by Leibniz and the Bernoulli brothers and others in the 1680s. So around 1671, Newton wrote his then unpublished The Method of Fluxions and Infinite Series, which was published quite a few years later in 1736. But in this work, he classified first order differential equations known to him as fluxional equations at the time into three classes. So in modern notations, these equations that Newton classified as fluxional equations, differential equations in today's language, were this ordinary differential equation dy dx equal to f of y, which is these days called an autonomous first order differential equation, because there is no dependence of this function f appearing on the right hand side of the differential equation on the independent variable x. Dy dx equal to f of xy is what is now called a non-autonomous differential equation. So it's a first order non-autonomous differential equation because there is x dependence as well as y dependence on the right hand side. And down here, this equation is nowadays called a partial differential equation because it involves partial derivatives of the unknown function u, which is a function of two independent variables, x and y. So after 5 years, Newton managed to solve his first differential equation, and in the same year, Leibniz introduced the term differential equation. Note the fact that Newton called these equations fluxional equations rather than differential equations. Leibniz wrote in Latin, and in his work, the term differential equations appeared in Latin, equatio differentialis. Many differential equations are much more complicated than the ones that you saw on the previous slide. So, for example, if you need to model the flow around a ball, what you will see is that there is a turbulent wake behind the ball, and how do you describe this turbulent wake using partial differential equations? So what you would need to solve this time is this set of partial differential equations called the compressible Navier-Stokes equations, which also arise in, for example, in modeling the flow around an aircraft or around a car. So you might be modeling the flow of air in a three-dimensional domain, omega. The quantities of interest are the density of the fluid, rho, which is a function of position, x, and time, and the velocity, u, which is also a function of spatial position and time. You might be given an initial condition for the density, rho 0 of x. You might be given an initial condition for the velocity, u 0 of x, and there may be an external force, perhaps gravitational force or some other force acting on the fluid. So then the equations appearing down here are this first order partial differential equation, which is basically conservation of mass, partial rho with respect to t plus the divergence of the velocity field multiplying the density, that is equal to 0, subject to this initial condition with this initial function rho 0. And then the second partial differential equation that you see here is in fact a set of three partial differential equations because it involves the vector function u, the velocity, which has three components. You see that I have indicated u in boldface notation, and f is also in boldface notation. So everything that is indicated in boldface are vector functions. So in fact, u is a three-component vector function. So altogether you have a set of 3 plus 1, so 4 coupled nonlinear partial differential equations. So this equation down here is conservation of linear momentum. You might have a boundary condition, perhaps the velocity field is equal to 0 on the boundary of the domain, and then there is an initial condition. And down at the bottom of the page you see that I have mentioned the name of Pierre-Louis Léonce, who is a French mathematician, Fields medalist, who managed to prove the existence of global in time weak solutions to the compressible Navier-Stokes equations in a monograph which was published by Oxford University Press. So then why might you be interested in the mathematical theory of numerical algorithms? After all, you could take your partial differential equation, you could bung it into some kind of engineering code and carry out computations. Why am I interested in the mathematical theory of numerical algorithms? You might cook up some kind of numerical algorithm, code it up, there's your code, and you stick in your differential equation into the code and solve it. Well, my point is you have to be very careful if you want to go down this line. So here's an example which illustrates that things can go wrong. So please read this text. The sinking of the Sleipner A offshore platform in Gansfjorden near Stavanger in Norway on 23rd of August in 1991 resulted in a loss of nearly $1 billion. As the platform collapsed, it was found to be the result of inaccurate numerical simulation. So what happened in the case of this offshore platform is that engineering computations using a numerical code were performed in order to simulate the load-bearing capacities of these pylons that hold a platform. And in these computations, engineers were unaware that the numerical method that we're using was underestimating the load-bearing capacities in these pylons. The stresses that were computed in these pylons were underestimated and the platform collapsed. So my point is, indeed, you need mathematical theory to understand the behavior of numerical algorithms, because if you understood why a certain numerical method is not capable of predicting certain physically relevant properties, then use this algorithm with caution. So the importance of developing mathematical theory to understand the properties of numerical algorithms was already understood in the early part of the 20th century. So what you see on this slide are the photos of Richard Courant, Carl Friedrichs, and Hans Levy, who wrote a very important and very influential paper, which was published in Mathematische Annalen in 1928. The title is On Partial Difference Equations of Mathematical Physics. So in this paper, which really is a pioneering piece of work, Courant, Friedrichs, and Levy laid the foundations of the mathematical analysis of numerical methods for partial differential equations. So the basic idea in the construction of numerical methods for differential equations is really quite simple. So let me just give you an example. So let's think of ordinary differential equations, and in an ordinary differential equation you might have a first derivative. And you remember that the definition of the first derivative of a function y with respect to x is given by this expression here. You pass the limit as the increment h goes to 0 in this fraction, where the numerator is y of x plus h minus y of x, and the denominator is the increment h. So another way of writing this limit is that the fraction itself without the limit is equal to the first derivative of the function x plus small o of 1, where the small o of 1 notation indicates that this fraction here in the limit as h goes to 0 converges to y prime of x, assuming, of course, that y is a differentiable function. So then, if you ignore the small o of 1, the left-hand side is not going to be equal to the right-hand side, but what you end up with is an approximation to the derivative. So if you scrap the o of 1, you have an approximation to the first derivative of this function y by this expression here, which is called the divided difference or difference quotient. If in your differential equation you have a second derivative, you can do the same. The first derivative of the first derivative is what the second derivative is. So if you repeated this difference quotient here, you took the divided difference of the first divided difference that you see here, you would get the second divided difference as an approximation to the second derivative. And by proceeding in this way, you can construct numerical methods by replacing derivatives by difference quotients. First derivative by a first difference quotient, a second derivative by a second difference quotient, and for partial differential equations, you can do this in the various coordinate directions. And by doing so, you have constructed what are called finite difference methods for the approximate solution of ordinary or partial differential equations, as the case may be. You may be familiar with Euler's method for the numerical solution of ordinary differential equations, which is based precisely on this idea that I described on the previous slide. So here's a differential equation: y prime of x is equal to f of x, y of x, subject to an initial condition, y of x0 is equal to y0. And the idea in Euler's method is to approximate the first derivative here by this difference quotient, and the right-hand side stays as it is. So what are these xk's that you see here? Well, in your interval of computation, starting from x0, you would create what is called a computational mesh by starting from the point x0, where the value of the solution has been prescribed to be y0, and you would step along in steps of h, where h is some chosen positive number. So then xk is the kth mesh point obtained by adding k times h to x0, and then over here on the left-hand side you have y xk plus h minus y of xk divided by h as an approximation to the first derivative at the point x equal to xk, and then on the right-hand side you would simply evaluate the right-hand side, f xk y of xk. So then this approximate equality serves as a motivation for the construction of a numerical method that we shall discuss later on in this course and explore its various mathematical properties for the numerical solution of ordinary differential equations. Well, numerical computations have gone a long way from these very simple considerations that Euler had in mind in his work. So let me just show you one example here, which concerns cosmological simulation of the evolution of the universe, and the simulation was performed by Volker Springler in the astrophysics department in Heidelberg, the University of Heidelberg, in a project called Millennium Extra Extra Large. In this project, they took round about 303 times 10 to the 9 particles over the equivalent of more than 13 times 10 to the 9 years, which is roughly the age of the universe, and they simulated the motion of these particles. So at the time when this computation was performed, this was the largest n-body simulation ever. It required the equivalent of 300 years of CPU time and used more than 12,000 computer cores on computer which has 30 terabytes of RAM. Computations were carried out in Germany on a machine called Europa in the Jülich Supercomputer Center. So I'll close this for a moment and I'm going to click on this. So what you see here is the numerical simulation carried out by Volker Springler. So while this simulation is running, let me just say a few words about what exactly we shall be discussing in the course. So in the very first lecture, I shall remind you of an important result from the theory of ordinary differential equations, which is Picard's theorem. Some of the assumptions that we see in the statement of Picard's theorem will appear in subsequent lectures as well. So after that first lecture, we shall move on to discuss some very simple numerical methods for the approximate solution of first-order differential equations subject to an initial condition. And we have already seen one such method, Euler's method, which is really the simplest possible example of a numerical method for the approximate solution of an initial value problem for an ordinary differential equation. We shall be interested in the construction of numerical methods, but we shall also be interested in the mathematical analysis of numerical methods for the approximate solution of initial value problems for ordinary differential equations. So at the start of the course, we shall be exploring numerical methods which are similar to Euler's method, and these are called one-step methods. An important class of these one-step methods are what are known as Runge-Kutta methods, and we shall spend some time on discussing these Runge-Kutta methods. So then we'll move on to a different class of numerical methods for the approximate solution of initial value problems for ordinary differential equations, which are called multi-step methods, linear multi-step methods. And here we shall discuss various concepts such as the stability of linear multi-step methods, the consistency of linear multi-step methods, and the convergence of linear multi-step methods to the unknown solution of the differential equation. A key result that we shall focus on in detail will be an important theorem called Dahlquist theorem, which brings together the concepts of stability and consistency and deduces convergence of a numerical method from the notions of stability and consistency. We shall also look at things like adaptive methods. So you have already seen a little bit from these slides that I showed you in this solid mechanics problem, in this fracture problem, an adaptive numerical simulation for a partial differential equation. Well, in this course, we shall look at much simpler situations. So we shall be looking at adaptive methods for initial value problems. And then in the final part of the course, we shall be discussing numerical methods for the approximate solution of partial differential equations, in particular diffusion type equations, parabolic equations such as the heat equation. So I shall be posting the slides of the lectures on the web pages. The problem sheets associated with the course will also be up on the web pages. There will be also a set of lecture notes that you will be able to download from the web pages, and these lecture notes cover the entire course with all the details. So if you miss anything in my lectures, please consult the lecture notes. The only other thing I wanted to say at the end of the lecture is, should you have any questions about any of the material that you find in the course, please feel free to contact me by email. So that's it for today. See you in the next lecture. Bye-bye for now.